In 2.3, we're going to talk about 3 different topics. The first is the definition of what it means to be differentiable. Second, average and instantaneous rates of change. And the last thing is an application of derivatives using position, velocity, and acceleration. So, first topic is differentiability. We're going to go through its definition. So how to tell if a function is differentiable. The derivative of a function only exists when 2 things occur. And the first thing is that the function is continuous. The second thing is when the slopes of the tangent lines from the left and right sides of any point approach the same value. So, in other words, we have 2 keywords we're looking for. First is that the function is continuous. The second, we simplify this by saying that it's smooth. So this is what we're looking for. Is it smooth and continuous? Then we have a function that is differentiable everywhere. Some examples. Let's take this function here. It's continuous. Let's look at a certain point. Let's look right here. So we'll call that C. This function is continuous. And it's smooth. We can see that the slopes of the tangent lines from the left and right side of this point approach the same slope. So if we take the slopes here, we have positive slopes that are getting less and less in value, and we're approaching the slope of 0. If we come in from the other side, they are negative slopes, but they're becoming less and less negative and approaching the slope of 0. They're approaching the same slope. So it's also smooth. So another example. This function is continuous. Let's look at specifically this point right here on the origin. It's not smooth. If we look at our slopes coming in from the left, they're becoming more and more and more positive. These ones are coming in, they're negative slopes. These ones over here will be positive, more and more and more positive. It's not smooth though. We actually have a sharp turn or a corner, which means we're definitely not differentiable here at 0. So since it's continuous everywhere but not smooth, it's not differentiable. Although it is differentiable everywhere else where it is smooth, it's only not differentiable here at this point. Our last example, let's say we have a rational function. And although it is smooth everywhere, nice, smooth turns, no sharp points, it's not continuous, of course. It has a discontinuity at the vertical asymptote. So it's continuous everywhere else except at the vertical asymptote. So it is differentiable everywhere else, just not here at the vertical asymptote. In part 2, we're going to compare the average rate of change to the instantaneous rate of change. You'll remember I talked about these two things in our Objective 1 note. The average rate of change was the slope of the secant line. On an interval, so we'll say on AB. And the slope works out to f of b minus f of a over b minus a. While the instantaneous rate of change was the slope of the tangent line. Which we know is the derivative. So we'll need to be able to recognize what we're being asked to do. If we're asked to find the average rate of change, we're just doing slope through 2 points. When we're asked to find the instantaneous rate of change at one place, we're being asked to find the derivative of a value. So let's look at a little problem. So starting with the average rate of change, of the function 3x squared minus 7x plus 1 on the interval -1, 2. Then we'll find the instantaneous rate of change. For the same function at each endpoint. So for part A, find the average rate of change. We're simply finding our slope, which is f of 2, that'll be b, minus f of -1 over 2 minus -1. We're just going to plug in these values here. So if we plug in 2 to our function, we get 12 minus 14 plus 1. If we plug in -1 to our function, we get 3 plus 7 plus 1. And it's all divided by 3. So this will work out to -1 minus 11 over 3, or -4. So this is our average rate of change on the interval -1, 2. So now let's look at the instantaneous rate of change, which is the derivative. So we want to take the derivative of our function. We get 6x minus 7. We're going to evaluate it at each endpoint. So we'll evaluate the derivative when x is -1, and we'll evaluate the derivative when x is 2. The y prime of -1 Negative 6 minus 7 is negative 13. And y prime of 2 is 12 minus 7, which is 5. Our third section is the application of derivatives, position, velocity, and acceleration. So we're going to start with our position function, which is s of t, or sometimes x of t, or maybe f of t even. And the way we get from our position function to the velocity function is by taking the derivative. So the velocity function, v of t, or we would say the derivative of s or the derivative of x. Okay. To get to acceleration, we take the derivative again, and we get acceleration. So a of t or the derivative of the velocity function, or at this point, we would have the second derivative of the position function. All right, so we're going to start with our position function. There's two formulas, and it depends on if we're measuring units in feet or in meters. If we're measuring in feet, s of t is negative 16 t squared plus v naught t, is our initial velocity, plus s naught, which is our initial position. If we're measuring in meters, s of t is negative 4.9 t squared plus v naught t plus s naught. Again, this is initial velocity and initial position. A few reminders. We have our average velocity, which is our average rate of change. So again, we'll say on an interval AB, and this would be S of B minus S of A over B minus A. So again, it just depends on what the function's called, if it's S, X, or even F of T, F of B minus F of A. So it's just the same thing. This is change in position over change in time. Versus our instantaneous velocity, which of course is going to be the same thing as our instantaneous rate of change. Or our derivative. So this is v of t, or s prime. So before we go on, a little bit about velocity and how it's different from speed. velocity has direction. So a positive velocity means we're either moving in the forward direction or to the right, or possibly up. A negative velocity means we're moving in the reverse direction, so to the left or possibly down. And then speed is just the absolute value of the velocity. The next part is acceleration. Just a little bit here about acceleration. Again, A of t, it's the derivative of the velocity or the second derivative of the position function. We also need to talk about units here. The position function is measured in feet or meters. When we talk about velocity, our units are measured in feet per second or meters per second. Then when we get to acceleration, our units change again. This is feet per second, or meters per second. For our last example, we're going to practice some position and velocity. So I like to use Mr. Scherer. He's a swimmer, diver, and used to coach water polo. All right, so the introduction to our problem, we have at time 0, Mr. Scherer jumps off a diving platform 32 feet above the water, and his initial velocity is 16 feet per second. A few things you want to pay attention to. First up are the units. This one's feet, so we're going to make sure that in part A, when we write our equation, that we use the equation for feet. So we're going to start with, write the equation for the position function. So I'm going to name it S of t is equal to negative 16t squared, so what we'll lead off with, plus v naught t. Now his initial velocity was given to us. We were told that it is 16 plus his initial velocity, initial position. Now his initial position is 32 feet above the water. So he's up at 32. So that's it. That's part A. Write the equation. The first thing we always have to do, even if we're not told to write the equation, is to write the equation. If we don't have one, we don't have anything to work with to solve the problem. Part B, when will Mr. Scherer enter the water? So when meaning at what time. You'll notice we have two variables here. S of t. So s is position, just like s naught is initial position, so s is position at a certain time, and then t time. So find the time means we don't know t, we must know his position. So when he enters the water, his position is no longer 32 feet above the water. He's now fallen into the water. His position is now at 0 feet. So find the time when the position is equal to 0. So we're just setting our function here equal to 0. So I'll start by factoring out negative 16. And we'll continue factoring. So we get either at 2 seconds or at negative 1 second. So it must happen after 2 seconds. All right, last. What is his velocity at this time? The time when he enters the water. So I want to know the velocity when t is 2. So first of all, I have my position function. I need my velocity function. My velocity function is just the derivative of the position function. So we'll get negative 32t plus 16. And then we just want to know his velocity at this time, so we'll plug in 2 for our velocity. That's going to come out to negative 48. The last thing we want to do is include our units, so just like we did here with time. And remember that velocity is measured in feet per second, just like our initial velocity was.